Hi everyone. In this video, we're going to be writing shear and moment functions for this awesome cantilever beam with a point load. So the prompt will say something like this, write V of X and M of X functions for this beam. Now, when you pronounce these out loud, right, please don't call this V sub X and please don't call this M sub X. If we wanted to use subscripts, I'm going to toss in some axes here, right? So here is X and here is Y. That means Z is coming towards us. What we're actually doing is we're doing shear forces in the Y direction as they vary with position X and moments about Z as they vary through position X. Okay, so you would say this V sub Y as a function of X and M sub Z as a function of X. Now, that's not too important for a statics class, but in more upper level courses, that type of distinction is going to become a little bit more important. All right, let us get to it. So the first thing we need to do, so our origin is over here at the left. And so what that's telling us is that we start our free body at A. We go some distance, X, and then we cut. At the cut plane, I introduce my internals. I want to draw those in the positive direction. So shear positive up, down. So shear as it varies with position X and moment as a function of X. So M of X, V of X, not M sub X, not V sub X. What's the other thing we need on this free body? Well, we need our reactions at A. So we disconnected the beam from the support. And so now we need to put reactions at the support. So we'll have A sub Y. A sub X is equal to 0, has the potential for a horizontal reaction, but it doesn't need one. And then we have an we have a reaction moment, which I'll call M sub A. Now, I cannot proceed with this prompt until I express the reactions in terms of the load. And so to get those reactions, I'm going to put this first free body on pause. And the free body I want is the entire beam from A to B. What's on the beam from A to B? Well, now I see the load P. And now I can solve A sub Y is equal to P upwards. And my moment at A, by inspection, it has to be counterclockwise to resist the tendency of the load to rotate clockwise, and it's equal to P times L. Go ahead and pause the video and write out the equation of equilibrium if you want to verify that. If you are ready to take that at face value, then you can keep watching. I'm going to move this way over here and then bring my other free body back. And I'm just going to update this and this with the new information. Hey, we are looking good. We are looking good. And after that, all we do is go to our equations of equilibrium. So in order to write the shear function, we want to sum forces in the y direction equals 0, upward positive. How many terms? 1, 2. First term, P upwards. Next term, V of X downwards, so a minus sign, and set it equal to 0. Therefore, my shear at any cut x is equal in magnitude to the load P, and the sign is positive up, down. So this is telling me that my shear, this is a function, but it happens to be constant. And I should probably add one other detail here. Should probably add one other detail. The domain of x is, so we're going to use a single domain. It's going to cover everything from x equals 0 to x equals L. And sometimes I get the question of why I'm not putting, less than or equal to, greater than or equal to types of symbols there. And the reason why is because we have jumps and discontinuities at the end. And so in some cases, our shear will be undefined. In some cases, our moment will be undefined. So it's safer just to do between those concentrated forces and concentrated moments. So that's a better way to note that. Okay, and now that we've got our shear function done, we're ready to sum moments about the cut. Again, why about the cut? Well, mathematically, you could sum moments anywhere, but I'm going to pick the centroidal axis of the cut plane because my shear function is coincident, and so I don't have to worry about any errors on my shear function carrying over to my moment equation. Okay, so we're going to sum moments about the cut. How many things are we going to have? How many terms in our equation? 1, 2, and 3. Let's go ahead and do that. So first term, PL, that's our reacting moment. In order to maintain equilibrium, that couple moment acts thumbs up, positive counterclockwise, give that one a positive sign. Next term, force P. That's my vertical force reaction required for equilibrium. Moment arm to the cut, distance x. Sign for that is going to be negative, that tendency to rotate clockwise about the cut plane. Last term, m of x, m as a function of x. That's what we want to solve for. And that one is counterclockwise, positive thumbs up, give that one a positive sign, set it equal to 0, and rearrange. As I rearrange, I'm going to want to order my terms in descending order of x when we get into these polynomials. This is less critical for statics, more critical for upper level classes when these equations get more complex, but we're going to get good habits in now. So I'm going to move p times x to the other side, and I wanted that to be my first term because it has an x in it, matching this x and this x. And my next term is a constant minus p times L. And that is my final answer for this domain. And this function at the end, so this is linear. So x, this is a linear function. So if I plot this, it's going to be a line. We can think about like y equals mx plus b, standard form to think about that. So it's going to have a positive slope, and it's going to have a negative intercept. Depending on when you're watching this video, you may or may not have already covered shear and moment diagrams. And this particular over here, this particular beam, shear and moment diagrams I can construct very quickly. I'm going to go ahead and do that. So my shear diagram, I start at 0, I increase up to P, I stay constant along the length, I decrease by P to get back to 0. Okay, so this is my 0. So I have positive internal shear force the entire way, and the equation of that line, there's the line, and that is the equation that expresses that function. Continuing on to the moment diagram, so there's my 0 line right there. Here's my moment function. The first thing I'm going to do at the left support is jump down because of the reacting moment, P times L. There's a discontinuity there. And then increase by the area of the shear diagram. That's going to get me back to 0 here. Since my shear is constant, my moment diagram is linear. That's because shear is the derivative of moment. Moment is the antiderivative or integral of shear. So this is my linear function. And if I did everything correctly, this line right there should be defined by that function. So let's spot check it. There's my intercept, minus PL. There's my slope. My slope is P. That's my value of the derivative function. So I know my equations are correct. All right, thanks for tuning in. Oh, by the way, if you haven't done shear moment diagrams left yet, and this last bit didn't make any sense to you, that's to be expected. You'll get there soon enough. Have a great day.